Alright, here we'll continue from last year's exam, starting off where we left off after the last session. So, the first question for today is going to be on the topic of K-cores. And the first sub-question is, what do we mean by the K-core of a network? Well, a K-core is essentially a sub-network of a given network that satisfies that, the requirement that all the nodes have a degree of at least 3. Of at least k. So if you want to look at this specifically for this network, first we can just write down the K-core of a network is a subnetwork such that all nodes have a degree of at least k and connect from their connections to the other nodes in the K-core. The fact that degree is at least k from the other nodes in the core is the key aspect of it. It's not just all nodes with a degree of at least k. So for instance, if we want to find the 2 core of this network, if we look at node E here, it has a degree of 2, but node F only has a degree of 1, and if we remove F, then E will only have its one connection to D left, and so then E will be removed as well, because now it only has a degree of 1. And that would similarly knock over to D, and then would remove D. And then the 2 core would be the remainder of the network. If we see like this sort of hourglass sideways shape here, A, B, C, G, H, that would have a degree of 2 with everything connected to itself. And that same applies here with I, J, K, L. But that's not the innermost core in this case. If we then try to go one further and we take the 2 core, the 3 core, by removing all the nodes with degree of 2, and then doing that recursively for all the new nodes that get their degree reduced to 2, we'll see that A and B have a degree of 2, so they go away. H as well has a degree of 2, so it will go away. Then C now, since we've removed 3 of its neighbors, will only have a degree of 1, so it will go away as well. And then G will have lossless connections to both C and H, since they have been removed previously, and so we will have to remove G as well. And then we're stuck with I, J, K, L, which is a fork leak, and where everything has a degree of 3. And from there we see it's pretty obvious that there is no fork leak because, a fork core, because all we have left here is a fork leak, and so nothing here is going to have a degree higher or equal to or higher than 4. In a fork leak, the degree of all nodes is 3. So the innermost core is IJKL. That's how we go about doing a K-core. In this network, it's pretty straightforward to do it visually. Of course, in a larger network, you would have to maybe rely on some sort of computer program. But in an exam, you're never going to have to do the K-core of a network where you can't do it visually pretty straightforwardly. Okay, on to the next. We're going to be on the topic of centrality. So here we see 3 copies of the same network, and the coloring of the nodes in each network is based on 3 centrality measures, or one of 3 centrality measures: betweenness centrality, closeness centrality, and eigenvector centrality, with red nodes being the most central. Which nodes match which centrality measure? And so the purpose of this exercise is to test you on the notion of centrality and how you're familiar with the different concepts. And so the idea here is that we see clearly that depending on the centrality measures, some nodes are more central and some are less central, and it's not going to be the same in each one. And so the question is, how can we relate what we see from the role of these different nodes, or the position of each of these nodes in the network, and the three centrality measures we're talking about. So for instance, if we look here at A, we see that the most central nodes here are the ones that are in the middle of the image, so to speak. That is not too surprising. We'll have that in B as well, and for that matter in C. That lies in the notion of centrality. But we'll see that we have this reasonably dense interconnector region here, where some of the secondary nodes in this are substantially less central. If we compare to B, the nodes in this densely connected region on the left will all be rather quite central, and there's not too much of a preference for the ones that are closer to this remaining bit here. In this case, it seems that the most central ones are the ones that are in this densely connected cluster, the ones that are connected to nodes that are themselves well connected. Conversely, here we see that being part of this densely interconnected group in C does not contribute anything at all. That doesn't help centrality. If anything, it looks like it's the other way around. The most central nodes are the ones that are in this intermediate position here. And what that means is that if we look at these centrality measures, between the centrality favors nodes that are located on closest or shortest paths, and typically that will really tend to emphasize the nodes that are located in bottlenecks in the system. And if we see these these colorings, coloring C is the one that matches here. The two that are the most central are the ones that are on this one link bottleneck, and with between the centrality, every path to these three here has to go through these two. And so that's why these two will have very high between the centrality. And so we see that for network C, betweenus is the correct one. If we look at closeness centrality, well, that's based on average distance to everything else. And if we can contrast it with eigenvector centrality, because these two are somewhat more similar, A and B are somewhat more similar to each other than they are to C. So yeah, eigenvector centrality specifically favors nodes that have central neighbors. Eigenvector centrality is something of a recursive or self-referential expression, in the sense that you have high eigenvector centrality if your neighbors have high eigenvector centrality, and your neighbors have high eigenvector centrality if their neighbors, including you, have high eigenvector centrality. That's the and that concept translates into an eigenvector problem. And the fact that highly connected nodes, the fact that we have this grouping of highly connected nodes that connect to each other and they're all central in this sort of dense region is compatible with this notion of eigenvector centrality. Well, if we compare it to closeness centrality, for instance, these two nodes on the left here, they are quite distant from the rest of the network, which will reduce their closeness centrality, but they're part of this interconnected group, which gives them high eigenvector centrality. And so we see here that in B, these are very central, and that means that B is eigenvector centrality, while closeness centrality is A, by both elimination and the fact that we see that the ones that have short distances on average to everything else in the network, the ones that are sort of visually very much in the center of the network in this layout, will have high closeness centrality. So closeness centrality corresponds to visualization A. Okay, similar exercise, just a different network. This case here is maybe even more clear-cut than the others. I will not dwell too long on the different centralities because we've just visited them. But here we see that on A, that the most central ones are the ones that are on these single connections between these different, I guess you can call them modules. I haven't run an actual module decomposition algorithm on this network, but we see that here we have a densely connected, I think it's an 8-clique then you have a fork leak in the middle, 2 3 leaks, and then not quite a fork leak on top here. And we see that the most central ones are the ones that sort of serve on this bridging aspect, the bottlenecks really. And that is very consistent with betweenness centrality, so that will be A. So here B, we see that the bottlenecks aren't that much more favored. If we contrast, for instance, this node here, which really doesn't lie on the shortest path to anything except itself, and sure enough, it has a very weak color here. Will still be quite central in the middle here, based on this. Meanwhile, this region here, sure enough, it has a certain amount of betweenness centrality because it is very close to everything else in this clique. There's our closeness centrality. They're very close to everything in this clique, but they're quite far away from a lot of other things. But the most prominent nodes are the 4 that are really in this central fork clique that lies between everything else. So B is going to be closeness centrality. Lastly, in C, we see that the most central nodes by this measure are the ones that are in this densely connected region where everything connects to each other. And as we discussed in the previous question, this fits very nicely with eigenvector centrality. So B is closeness, A is betweenness, yes, and C is eigenvector. And there we go. Okay, so the question here is, which of the following measures may be computed if all one knows is the adjacency matrix of a network? So the assumption is you have a matrix, a network that you want to analyze, but all you have is the adjacency matrix of a network. You don't have any visualization of it. You don't have any site escape file with node attributes and so on. All you have is the adjacency matrix. And which of these measures can you find out from that? And now this is a bit of a trick question in its phrasing, because the thing is, an adjacency matrix encodes all the information from a mathematical perspective of the network. From an adjacency matrix, we can plot out the network in full detail. We might not have any visualizations, but visualizations aren't that important really if you're going to do analysis. They let you at a glance have a look at a network and see what it looks like, but you don't use the visualization to compute any statistics. In fact, all the statistics you can imagine from a network, unless you have statistics that depend on secondary node attributes, can be computed directly from the adjacency matrix. So for instance, the maximum k-core, you can find that out from the adjacency matrix, because k-core only really depends on the degree of the nodes, and that is indirectly encoded in the adjacency matrix. Similar, well, degree, yes. Both centralities, because again, they only depend on the topology of the network in terms of what is connected to what. And clustering and assortativity. All of these measures only depend on which nodes are connected to which, and the adjacency matrix really does just encode that in its entirety. So everything here is actually true. So okay, on to the next question. So on the top of a gene co-expression, what are the steps in creating an unweighted network from microarray gene expression data? So the first step is you want to convert two vectors of gene expression data, you want to convert gene expression data into something that is a gene-to-gene score. So you want to say, compute gene pair scores, weights for each gene pair in the data set. Typically, this will be done through correlations. So you will take the expression pattern of each gene and then correlate it to the expression pattern of every other gene. This is done by correlations, Spearman, Pearson, between the gene expression vectors for each gene. But you can also use other measures, things like mutual information or weighted topological overlap as a secondary step after the correlations. But first, you need to compute a set of scores for each gene pair, and then 2, find a suitable cutoff or threshold value, and then you just remove all the gene pairs, or the connection between gene pairs where the score found in 1 is lower than that value, and remove all links where the score from 1 is below the cutoff. This is necessary because when you do the original weighted scoring in 1, you get a complete network. Everything is connected to everything. And if you're going to turn that into an unweighted network without filtering anything away, you're going to get a very boring network. If you have your network is an n clique, say a 2000 clique, you're not going to get any information out of it. That's it's just going to be a jumble. So what we need to do is we need to find a cutoff. Say, for instance, a correlation that corresponds to a desired p-value for the number of samples that we have, and then from there we just say that, okay, we want to have a p-value of below 0.05, and we can find out from formulas what correlation that corresponds to for our given sample size, and then we just discard all the correlations that are weaker than that. And that brings us over into question B. So what do we mean by correcting for multiple testing, and why is that important when we're building gene co-expression networks? So multiple testing is something you need to do whenever you are conducting an experiment and you're testing multiple independent hypotheses. The example I use in class is from the comic XKCD, where they test, where the notion is, do jelly beans cause acne? And then they say, and then they test that, and they find that jelly beans don't cause acne. And then it's like, oh no, but it's a specific color. And then they test 20 different colors, and sure enough, in one of them they find, with a p-value but less than 0.05, that green jelly beans cause acne or something like that. But if you understand p-values, you'll know that if you try 20 different experiments, even if they are all, even if the null hypothesis is invalid in all of these experiments, one of these will actually return a p-value below 0.05. That is how p-values work. And so you need to, if you're going to validate a hypothesis with reasonable confidence, you actually need to be to increase the strictness on your p-value in terms of rejecting the null hypothesis. So we can say correcting for multiple testing involves adjusting the p-value for rejecting a null hypothesis when you perform a large amount of independent tests. And so why is this important when we're building a gene co-expression network? Well, in any typical gene correlation set, you're going to find, you're going to have at least a few hundred, typically thousands of nodes correspond to the different genes in your genome. And you're going to be computing correlation scores between all combinations of this. So if you say have something like a human genome where you'll have in the ballpark of 20,000 genes, maybe even more depending on exactly what types of genes you're filtering away in your original set, you'll have 20,000 squared divided by 2, which is 200 million different gene correlation pairs. And when you're going to compute 200 million scores, some of those are going to be almost perfectly correlated if you have very few samples. For instance, if you have 6 samples per gene, 6 measurements per gene, the chance of 2 completely independent sets of, or sequences of 6 numbers being perfectly correlated, even though they're generated at random independently from each other, is 6 factorial, which is 720. So if you have 6 samples out of, and there's a 6 measurements per gene, and you have a 1 in 720 chance of any 2 of them being perfectly correlated, if you do 200 million tests, clearly you can imagine that quite a lot of them will have a perfect correlation, and that is obviously a very large problem. So that's so typically what you will need is you'll need to have a much higher number of samples, so that perfect correlations or very strong correlations don't happen that much. But the notion is, for instance, if you have even if you have say 20-30 samples and the p-value to a score of 0.5 for 2 gene sets of length 20, if the p-value for correlation of 0.5 there might be say 0.01, individually at a glance that seems significant, but when you're returning 200 million pairs that are tested, you are going to get a bunch of false positives. And so in general, to summarize, we can say that for gene co-expression networks, multiple testing is important because we test we compute correlations for all gene pairs, which is usually a very large total amount of correlations, approximately for 200 million for a set of 20,000 genes, for instance. This means that a gene pair with a correlation with p equals 0. That correlation with p equals 0.01 that correlation with p equals 0.01 for an individual test will likely show up about 2 million times, even if the genes are all uncorrelated. And so because of this, obviously you need to adjust your correlation cutoffs to have much stricter p-values than, for instance, p equals 0.01, due to the very large amount of sets you have. Okay, next question. So, next question is on the topic of components versus communities. And so the question is, what's the difference between the term connected components and communities, which are also sometimes called modules, in an undirected network? And which of the two are the easiest to identify, and why? Well, so a connected component is a subnetwork, or is a subset of the network, where every node can be reached from another by walking over edges. And so, in a if you have two different connected components, that means that there is no path from the one to the other. In a community, the requirement isn't that strict. A community is simply a set of nodes that has a substantially higher number of internal connections between the nodes in the community than it has of external connections that it's outside of the community. Contrast that to the connected component, where in a connected component you only have nodes, you only have connections within each connected component. If you were to have something like two different connected components, and you were to add an edge between any two nodes from separate connected components, well, those two connected components would merge into one larger connected component. Well, for a community, this is not necessarily the case. For instance, if we return to this, we can say that these different groupings here constitute different communities, but if you were to add, say, an edge from here to here, that wouldn't necessarily change a great deal in terms of the topology of the network. Or in the community division of the network. So, connected components consist of subnetworks, are subnetworks where all nodes can be reached from all other nodes in the same connected component. Communities modules are subnetworks where nodes are more connected within the community than to the outside, but outside connections are possible. So which of the two are the easiest to identify? And let's say we can just say here, with no connections to nodes outside the connected component. And note that a connected component doesn't need to be particularly dense. You can have a connected component where, if we look for instance here, everything here is part of the same connected component, even though node F is really quite peripheral and not densely interconnected with the rest. Oops. And so the question of which is the easiest to identify of connected components and communities, it's connected components. Because connected components, it's a very strict, clear-cut binary definition. You can essentially find it by just starting at any random node, and then looking at all its neighbors, adding them to the connected list of the connected component, and then go through all their neighbors, and so on until you run out of nodes. And that's the burning algorithm that we talked about earlier, and it runs quite fast. And it's a very, there is nothing you can contest about a connected component division. They're extremely unambiguous. Meanwhile, communities are a lot trickier to find, because it's not as binary, right? You can have, if you look here, it's kind of hard to tell whether, for instance, actually in this one it's not that tricky. You can say the connected components are quite straightforward. Actually, we can say, look at this node here, right? Which community should that node be a part of? Should it be part of this for clique here? Should it be part of this for group up here? Maybe all of these should be a community. It's since the fact that a node can or can't belong to community is a lot vaguer than in the case of connected components, it's a lot harder to find connected component or communities in an efficient way. For a given community composition, we can score it and we can compute the modularity, but there's no guarantee that this community composition is the one that has the highest modularity. And any exhaustive search of possible decompositions would take far too long. So connected components are the easiest to find since the borders are clearly delimited, while borders between modules are often fuzzier. We can generally summarize it like that. Alright, next sub-question. Or next question. And now we're sticking on the topic of components, but now we're going on into directed connected components. So in a directed network, we can identify weakly connected components. A weakly connected component can in turn be divided into three substructures that together form what we call a bow tie structure. And so the first question is, what are the names of the three substructures? These are the in component. Well, first of all, we can start with saying what a weakly connected component is. A weakly connected component is what you would get, or the set of nodes that if you were to convert the unweighted network, the directed network into an undirected network by just converting any unidirectional edge to a bidirectional edge, it would correspond to the weakly connected to the connected component in the undirected network. So, for instance, if you look at this network here, if we were to just turn this into a undirected network by just keeping all the edges but removing the direction, we would see that this forms a single connected component, and that would be the weakly. And so that means that this entire set of nodes forms a weakly connected component, because if we map it over into an undirected network, it forms also a single connected component. And so the three substructures within this weakly connected component are the in component, nodes which can reach the other well, and we can't really go through this in order without getting a little bit ahead of itself, but the in component are the nodes from which you can reach the strongly connected component and the weakly and the out component. Actually, we can start with the strongly connected component. So the strongly connected component, and we're not asked to explain what these are, but I will here for the sake of thoroughness. The strongly connected component is a set of nodes where there are paths to and back from all other nodes in the strong connected component. It's a little bit of an unwieldy definition, but essentially it means that it's the set of all nodes where from one node you can reach the other, and from the other you can reach back to where you started. All nodes for which you have such paths where you have essentially cycles that can loop you back, those form the strongly connected component. The in components are nodes from which you can reach the strong CC, but you can't return from the strong CC to the in component. Lastly, we have the out component, nodes that can be reached from the strong CC, but you can't return from the from the out component to the strong CC. So, and that sort of forms a bow tie structure. So we can consider it as the center of the bow tie is the strongly connected component, which is essentially a set of loops that go back on themselves, because you can always go to somewhere and then back to where you started, and that would form a loop. And the in component is everything that sort of feeds into that, a tree essentially that feeds into that, and the out component is a tree that feeds out of that. And so if we look at this network here, we can actually identify these nodes, and maybe that will make things a little bit clearer. And so the first substructure, I'll pick the in component for that. Of course, the order here doesn't matter, but as long as you're consistent about which nodes go into which. And so, okay, the question here is which nodes are part of the sort of first one-way thing, that once you leave that node, you can never return to it. But you can still continue down the network. Obviously, A only goes out. So A is obviously not going to be in anything but the in component. So we'll say A. Similar, G also only goes out, so G is going to be in the in component. See that F also, it only goes out to D, but then the only thing that goes into it is G, which is in the in component. So F itself is also going to be in the in component. So we can go F. And lastly, D. We see here that D gets connections in from A and F, but they are also only in the in component. And if you leave D, you can't really, since you can't return to either A or F, since they're in the in component, you can't return to A or F once you leave D, and so you can't return to D. And so D itself is going to be also in the in component. Meanwhile, if we look at C here, well, from C you can go to I and back. So C is not in the in component. Obviously, I isn't going to be either because we have a loop here. If you look at B and E, actually C, I, B, and E, we see that they all form. You can reach either of these from any of these, because you can go from, if you want to go from B to C, sure, you don't have a direct B to C connection, but you can go B, E, E, I, and I, C. Similarly, if you want to go from I to B, you can do that by I, C, B. We have here essentially a 4-cycle, I, C, B, E, and back to I, which means that these four at least form a strongly connected component. So we can start with there. Strong, C, C, B, C, I, E. And that only leaves us J and K. And we see that J and K don't have outgoing edges. And so you can't reach back, you can't go anywhere from them. So they're definitely not going to be in the strongly connected component. They're not going to be in in component either, because you can't go out of them. You can't reach the strongly connected from them. You can't reach anything from them. And so J and K form the out component. And these are the three substructures in our network. We have the in component, A, F, G, and D. That is this sort of first unidirectional segment where you lead into a strong component. The strong connected components C, I, E, and B. Here you can go around and around as much as you want. There's no like direction per se to it. But then once you leave out from J and K, then there's direction to it. You can't move back anymore. And so these are the three substructures or types of substructures within the weakly connected component as it applies to directed networks. And so this also shows that don't take this bow tie structure too literally. Now I could have chosen a layout where we move D, F, and G outside to the left, and then we could draw this as something as a bow tie, but again, I don't want people to hang up too much on the visualizations, because that can often be quite deceptive. Alright, Next and second to last question for this session. The topic is going to be the Barabasi-Albert model. And the first sub-question is, describe how a network is generated with a Barabasi-Albert model. So, we start with a set of connected nodes. We can call it just a k-clique. You can start with more than k. You can start with sort of whatever you want, but you need to start typically with at least a k-clique, where k is actually a parameter of the Barabasi-Albert model. And then we add nodes one at a time with k new connections. These new edges go to already existing nodes with a probability proportional to the degree of that node so far. So for instance, we can start, if we set k equals to 3, we start with a 3-clique, everything is connected to itself, or 3 nodes where everything is connected to everything. Actually, we could start with a 4-clique if we're going to choose k equals 3, so we can say k plus 1 clique. This first part here is not super important. And then we add we'll add a 4th node with degree 3, and that one is going to connect to everything else. Fine, now we have a 4-clique. Now we add a 2nd node with degree 3, and now not everything is going to be connected to, so we just pick 3 of the 4. They all have the same degree so far. So we pick 3 of the 4, and then we connect that new node to that to those 3 nodes that we picked. And then we add another node, and we do the same thing. We attach the new node to the existing nodes, but the ones that are the most connected so far are more likely to get these new edges. And this is a self-reinforcing effect. And we call that preferential attachment. So we can actually say, just say preferential attachment in parentheses here so far. And then you just do that until you have the desired number of nodes. The model itself is sort of quite simple in terms of how it's run. So what are the most significant properties of the Barabasi-Albert model? Well, the first is BA networks follow a scale-free distribution, scale-free degree distribution. Degree distribution follows a power law. This means that a few hubs are very highly connected, and there is no fixed upper bound on possible values of k. Essentially, with scale-free networks, we can have some very highly connected hubs in ways we're not going to find in, for instance, an Erdős-Renyi network, where we follow a normal distribution, which falls off much faster, and which is much more even. In a BA network, you're going to have a lot of nodes that are poorly connected and a few that are very highly connected. And from there, there's a few other aspects that follow from that. Some other characteristic: ultra small world. Shortest paths are shorter than in similar ER networks, for instance. No percolation or epidemic threshold, reasonably low clustering. These are, I'd say that these are off the bat some of the things one should know about a Barabasi-Albert network. Obviously, there's tons of other properties as well, but you don't need to be that exhaustive. The most important one really is this notion of the scale-free degree distribution. That is what the Barabasi-Albert model was made to explain. So on to the last question, and here we're talking about identifying bipartite networks. So here we have 5 network visualizations, and the question is, which of these can be considered to be bipartite? Bipartite, that's a strange word to pronounce. So before we actually go through these networks, we can just remind ourselves of the definition of a bipartite network. And there's 2 ways of phrasing it. Like, the first intuitive one, and a little bit more inaccurate, is a network which consists of where we can divide the nodes into 2 different classes or 2 different families or groups or anything like that, and you can only connect 2 nodes in the other group. You have no no connections to the numbers or to the nodes in your own group. For instance, if you were to do something silly like make a network from numbers, and you say that you add an edge between everything that is between any two consecutive numbers, that would be bipartite, because there are no odd numbers that follow each other, and there are no even numbers that follow each other, right? Even numbers would only be connected to odd numbers and vice versa. And so that would be an example of a bipartite network. The stricter, more formal definition is that a bipartite network is a network in which there are no odd length cycles. That means paths that return you to where you were. That means that if you want to walk around on your network and return to your starting points, you always need to take an even number of steps. And that is the formal mathematical requirement for satisfying a network being bipartite. And so if we look here, we can start with the easy ones. If we look at A, here we have some 3 cliques, right? Or 3 cliques within our network. And first of all, that is intuitively in violation of the first criterion, that you can set nodes into 2 different families, and you cannot have interconnections between, like inside a family. Because here, these 3, there's no way of dividing these 3 nodes into 2 groups where you only have connections between nodes of separate groups, because all 3 are connected to each other, which means that you need to put 2 of them in the same group, and that would violate the requirement. So obviously A breaches the more intuitive definition, and also here, for instance, we would have these 3 cliques. You have cycles of length 3, like 1, 2, 3, or even then you could say, I think all the non-redundant cycles here are of length 3 or 4. I mean, you can still have even length cycles in a bipartite network as well, right? In a non-bipartite network, we can have 1, 2, 3, 4. But as long as you have at least 1 cycle of odd length, such as 1, 2, 3 here, then you can't have a bipartite network anymore. Similarly, if we look at D, or conversely, if we look at D, we see here that it fits quite nicely into this notion of you have 2 families. And you have the left nodes and the right nodes, and the left nodes don't connect to each other, the right nodes don't connect to each other, but right nodes connect to left nodes, and left nodes connect to right nodes. And so D actually fits quite nicely with a bipartite network. And if we look at it more specifically, we see that the only cycle we have here, if we want to be formal about it, is this sort of, again, hourglass shape thing, which is a 4 cycle, but that's the only cycle you have. So D actually can be considered bipartite. What about the rest? Well, here we don't see any like sort of clear division between 2 groups as we do in network D, but we can rely on this formal definition that there are no odd length cycles. And sure enough, in B and E, there are no cycles at all. The only way you can return return to where you started if you're going on a random walk is by backtracking your steps, and that would of course give you an even number of total steps in any sort of path you take. And since there are no cycles really outside for the trivial back and forth, then B and E of course are strictly speaking bipartite. You could rearrange these networks in such a way that they form two nicely, neatly divided groups like in D, and you only have connections between the groups. Because since there are no cycles, there are no odd length cycles, trivially. So B and E, similarly. Lastly, looking at C here, now C does have a cycle, but again, since we've discussed the fact that it's odd length cycles that cause a network to not be bipartite, well, we can just figure out how long the cycle is, because this, of course, is a very regular network. And so all the cycles, you have multiple sort of different cycles. You have essentially one possible cycle for every start node, or two if you reverse directions. But they're functionally really the same, right? We haven't labeled our nodes. So all we need to do is really just count the one and then see if that's an odd or even number. So if we start here, we can start to say 1, 2, 3, 4, 5, 6, 7, 8. That's an even number of steps. And so, since that is, all the cycles here are going to be of length 8, and then C is also, it can be considered a bipartite network. And here we go. Here's all networks except for A can be bipartite, even though B, E, and C at first glance don't really look like what you would expect from a bipartite network. So yeah, that is it for now, and I'll come back again later with the rest of the exam, where we're going to be looking at metabolic modeling.